first place. So everyone knows that GPUs are pretty busy when running large language model workloads. And when we look at the die of a GPU, we can find several components. And we know that all these components, such as the CUDA cores, the on-chip network, and the memories are being saturated during inference and training. But there is one small component we find it idle the whole time, and that's the video encoding engine, which is composed of encoding and decoding pipelines of video codecs. And such phenomena leads us to think, since we got it for free, can we make it any useful? But before we show you the usefulness of video codecs, I want to give you a little bit more context about exactly what's being involved in the large language model training and inference. So here we have one GPU, and the basic is that for inference, the weights and the KB cache inside the memory of need to be stored inside the memory of the GPU. And for training, we also have to maintain the gradient as well as have some rooms for the optimizer states. But one GPU often isn't enough, and we usually have a data center of GPUs to parallelize and accelerate the computation. So suppose we have 4 GPUs here. In the most basic setup, we split the model across 2 dimensions, by data parallelism and pipeline parallelism. However, this requires communication between GPUs, which can be expensive in terms of performance, hardware cost, and energy. And in this example, we have 2 data parallel rings and 2 pipeline parallel rings, which means that we must transfer activation between pipeline stages, and if we are doing training, we also have to backpropagate the gradient and gather the weight gradient after each training step. And even in such a small setup, we have to communicate both horizontally and vertically. To make this clear, the data communication at each step includes the activation for each and every token at every layer, as well as the weight gradients of the entire model. And when we scale to a data center with thousands of GPUs and scale to models with hundreds of billions of parameters, such communication can become a major bottleneck. Therefore, the logical next step is to explore compressing this data directly to reduce its footprint and alleviate these bottlenecks. And plenty of researchers have been done on this topic. However, most of the existing approaches only focuses on a subset of the whole spectrum. For example, we have GPQ, AWQ doing weight-only compression. We have the Quarrels and QServe that extend this compression to KB cache. We also have the 1-bit series of optimizers like the 1-bit Atom and the 1-bit Lamp. But one great thing of our LLM.265 is its generalizability, such that it works for all types of tensors, which means that we only have to maintain one software stack to compress everything, which greatly simplifies the system design. And in addition, our method also achieves better information efficiency compared to existing works that's specifically designed to run one or two types of tensors. And such that our method can compress the model to be a smaller number of bits while allowing the same or even better model level accuracy. And after we have discussed this, one thing that comes to our mind is why video codecs work at all. Why does something that's originally designed to compress video footages work for Tensor that seems totally unrelated? So video codecs are extremely complicated monsters taking decades for humans to finalize. So here, I can only give you a very simplified version of it as a background. You can always refer to our paper for more details. So for a video codec, the input is raw video frames and the output is a compressed bitstream. And there are multiple stages of pipeline that connects the input to the output. So one stage is the CQ partitioning that smartly partitions the frames into microblocks. And after that, we have a JPEG-like transform and conversation pipeline that serves the backbone of the codec. What's making video codec stand out from a typical JPEG compression is the prediction stages it contains. And basically, the idea is that if you can predict, then you don't have to store everything. And 2 levels of predictions are being explored. The intra-frame prediction works for pixels that can be predicted within the frame. And we also have the inter-frame prediction and the Gaussian estimation, which works in a similar fashion, but pays more attention to the pixels that can be predicted from adjacent frames. So let's do a quick test to see if the video compression works. Say that we have a sample tensor, sample from the Llama model's weight, and it is quantized to 8-bit integers first. And let me define the rules here. So we will be gradually compression stages from the video codec to form a pipeline. And some of these stages is lossless, and some of them is lossy. And our rule is that the mean square error, the MSE of the compressed result, should be within 0.1 from the original raw format. And we will show the minimum number of bits per element that a certain pipeline takes to achieve such goal. And basically, with this setup, the lower number of bits to store the same amount of information, the higher the information efficiency of that certain pipeline. Okay, so let's start adding stages. We first add the entropy coding stage. And in this stage, the average bit width per element is reduced from 8 bits to 7.6 bits. And because with entropy coding, you can remove some redundancies in the distribution of singles. Then we add the DCT transform stage, and this is when the compression becomes lossy. And because it is lossy, we have plenty of gains in reducing the bit width from 7.6 bits to 3.5 bits per element. And then we have the intra-frame prediction coming in, which gives us another gain of 0.6 bits per element. And after that, adding the CQ partitioning gives us another gain of 0.3 bits. And unfortunately, that's where things stopped. And if we add the interframe prediction and motion estimation into the pipeline, not only do we not see anything, the information efficiency even getting worse, showing that the interframe prediction and motion estimation does not work for tensor compression. So we showed an overview of how each stage contributes to the compressibility of tensors. Let me give you two more concrete examples. And this first example is about why DCT transform work. So let's look at the distribution of values in large language model workloads. And typically, as plenty of researchers have shown, this distribution resembles a normal curve centered at 0 with long tail outliers on both sides. And prior works have consistently observed this pattern in the distribution of weights, activations, and also other types of tensors. And these outliers are problematic for quantization and compression algorithms because they have a high variance and they occur sparsely, which makes them hard to encode. And video codecs address this issue using a step called the discrete cosine transform. And on the right side, we can see after the DCT transform, the outliers have been removed, resulting in a clean and smooth distribution. And let's look at another example of one small block of values at the bottom left of the page. And we can see that an outlier with value of 128, and this outlier just disappears after we have applied the DCT. And we can verify the result on the right side that the block no longer contains any outliers. And essentially, what the DCT does is that it migrates the encoding difficulties from the outlier to adjacent positions within a block. As a result, the transformed data is much easier to quantize and much easier to encode compared with raw values. And another example why video codecs works for tensor is a little bit more tricky, but also more effective than the previous one. And let's take a look at the block of values from the weight tensor in the Llama model. And if we look closely, we can observe horizontal patterns like lines in the tensor. And this happens because each row in the block represents the weight within the same neural network channel. And higher studies have often shown that values within the same channel tend to have similar scales and varies only slightly. And this phenomenon is often called the channel-wise distribution in neural network models. What's coincidental is that video codecs are specifically designed to compress images that show similar patterns to tensors. For example, the image often have lines or regions with continuous colors, and video codecs are optimized to encode these patterns with intra-frame prediction. For instance, if an edge is detected, instead of encoding all the values in a row numerically, the video codec can just represent it as, well, there is an edge with black value at the 7th row. And this will save a significant amount of storage space compared to encoding each individual pixel. And in most of the cases, the intra-frame prediction is not perfect and usually leaves some residuals to encode. But that's okay because after the prediction, the residuals are much smaller in scale and much easier to compress compared to the raw values. Okay, great. It's finally time to show some real results about using video codecs to compress large language models. As we have mentioned earlier, LLM.265 works for various types of tensors. And let's begin with the model weight quantization and compression. And here, our method is evaluated along other compression approaches, including the GPTQ and AWQ. The results for our method, so let's first take a look at the PIQ data set. So the x-axis is the average bit width per element, and the y-axis is the evaluation accuracy. And from these curves, we can see that our method achieves excellent accuracy retention even at lower bit widths, so that accuracy comparable to the 4.25 bits baseline from the GPQ and AWQ, but our method only requires 2.65 bits per element, showcasing our method's exceptional information efficiency. So one unique feature of the video codec here is that it got versatile bitrate, which means that this allows us to have a fine-grained control on the storage budget. While existing method almost always relies on quantization into integer number of bits, but for our LLM.265, we can set a fractional bitrate. It could be 2.65 bits per element, or 3.1415 bits per element, or any real number. And such versatility enables us to have a finer grain control over the trade-off between the accuracy and the footprint. More importantly, related works like GPQ and AWQ all requires input data-aware calibration, which means that a carefully chosen dataset needs to be used to calibrate the quantization and compression process, making the quality of the compressed model data-dependent and fragile to change in input distribution. And although our method is purely data-independent, making it more robust and easier to deploy. And you can, so we have talked about compressing the weights. How about compressing the activation and the KB cache? It turns out that our video codec achieves the state-of-the-art information efficiency for KB cache and activation compression, and we have compared our approach with other state-of-the-art schemes such as the Poirot, SpinQuant, and running to nearest in the figure at the right side of the page. And from this figure, it shows that our method achieves the best accuracy among all these existing works. And being able to compress the KB cache is extremely helpful in a distributed inference setting, as the communication size between pipelines can be greatly reduced. And more importantly, if we still remember from the original line shot that the video codec is hardware accelerated, and this makes the communication compression between GPUs for a distributed inference setting even more efficient. And after testing the inference, we have also modified the deep speed framework to test our video codec on distributed training settings. Like we have talked about before, there are pipeline parallel training and data parallel training. So for the time's sake, we will only be looking at the data parallel training here. You can always refer to our paper for more details about pipeline parallel training. So for data parallel training, it requires us to compress the weight gradient across GPUs. Here, we train the PyZia 0.5 billion model on 4 GPUs with weight gradient compression enabled, and this plot shows the convergence curve for the training set. And we also compare our method with other compression baselines, such as the 1-bit add-in and 1-bit LAM method. And our result shows that while my baseline compression method requires 3.3 bits, our method achieves better accuracy, better convergence than baseline, requiring only 1.4 bits per element. And this is very surprising information efficiency, and that even if we compare with uncompressed baseline, if we want to maintain a comparable convergence rate with the uncompressed baseline, our method only requires 2.6 bits per element, and this leads to more than 6 times compression ratio compared with the original 16-bit floating point numbers. At the end, I would like to present some results and some insights we got from our work. As computer architects, we must now be very curious about the hardware cost of the codec. So let's compare it with other devices in a large language model infrastructure. First, this is the die of an RTX 3090 GPU with a die size of over 600. And here's the die of the Mellanox CS5 network interface card with die area of 170. And comparing with them, here's the die area of the video encoder and video decoder, all still do have a total throughput of 100 gigabits per second. And both their area is below 1 millimeter square, which is only a small fraction of the die area of other devices. And furthermore, when we look inside the video codec, we see that the majority of the die area of a video codec is spent on the interface prediction. And recall back from our earlier slide that interface prediction only works for videos and does not work for tensor compression. So in theory, we can remove these portions to make the codec even more smaller and even more energy efficient. And I think that leads to a straightforward question that can we modify the codec to do anything better? And Based on our observation, our proposal here is a new design called the Trinity Codec, which merges the compression pipeline of tensor, video, and data into one pipeline. And inside is that these three compression pipelines share many common stages, and reusing hardware is always beneficial. Going into more details of this Trinity Codec, we know that the interface prediction does not work for tensor, and we know that there is an upper limit of the demand for video decoding in equal. And given that, our design decides to augment the tensor pipeline for throughput while leaving the video-specific pipeline stages minimal. And notice that this is much better than simply duplicating the video codecs, because now we only need to augment the stages that works only for tensors, which makes the whole implementation more efficient. At the end, we simulate and evaluate our approach in a large distributed training infrastructure. The result shows that as the model size gets larger and larger, and when the data set size scale gets larger and larger, the gain introduced by compression will increase as everything scales up. And this observation concludes my talk, such that when the models are getting so large, the gap between the compute and the bandwidth are becoming even larger. And with compression, you can convert a portion of compute into effective bandwidth, which becomes a trade that gives more and more benefit over time. And in short, the more you compress, the more you save. We envision future hardware AI accelerators to come with building codecs for tensors, such that they have a smarter approach to scale their bandwidth. And that being said, NVIDIA, you should be building more codecs. And that concludes my talk. Thank you for your attention, and I welcome any questions.
Any questions from audience?
So I have one question. Do you have any inference still updating this?
That's a great question, because that comes back to our last sentence that NVIDIA should be building more codecs. So currently, because NVIDIA doesn't really have the demand for such high bandwidth video codecs, so any existing GPUs, we don't see any speed up, because the bandwidth, what's already available on GPUs are pretty limited.
And then another question here is that the biggest challenge is, either way, I'm from Apple, and then already it says no information. Apple is using video codec to compress that, so we are using that. The biggest challenge I see with the codec-based compression is that the streaming implementation is tough with the video codec, because you need to stage a certain sufficient large information first.
Yeah.
Because that's how video could work. If we use group quantization with things, we can do streaming for at least 64 numbers and so on. So do you envision that not being able to do streaming and get a different style can be a little bit of a challenge there? You follow my question?
I think there are a lot of things going on here. So first, for our method, we are still relying on 16-bit floating point computation. So the codec compressed format is only an intermediate format for saving the footprint space or saving the bandwidth.